Hello everyone, and welcome back to another video example. In this video example, we are going to do a complete linear analysis of a 4-node quadrilateral element. So up until this point, we kind of talked about the finite element method in chunks. We talked about isoparametric elements, we talked about solid elements, we talked about nodal forces, but we really haven't had the opportunity to kind of bring it all together to show you guys what Abacus, ANSYS, or whatever finite element program you're using, what it basically does in a global scale. And that's the kind of the goal of this example right here is we're going to take an element that is now being shown on screen and we are going to do a complete linear analysis. So if we look, we have our elements, we have our element geometry, we have our loading parameters, and basically what we're going to do is we're going to figure out the nodal displacements of the element, and then in addition we are going to use those nodal displacements to find things such as the stress, the strain, and the displacement inside of the element itself. This is something that often gets overlooked when we're teaching the class, in that once we find those nodal displacements, we usually say, all right, we're good to go. But actually, with those nodal displacements, we can do so much more, such as finding the stresses and the strains inside of the element. And that's kind of the goal of this example here, is I want to show you guys what exactly Abacus, ANSYS, or again, any other FEA program you're using, what exactly it does throughout its whole analysis. So that's going to be the goal here. Now, quick disclaimer, of course we are just doing one simple element. This will make things much simpler, but this process applies to if we had 1,000 elements. So that's kind of the takeaway here. It doesn't matter that we're doing one element. If we had 1,000 elements, the process is going to be exactly the same. Now this video is actually going to be a two-part video. All right, a two-part video. And the reason why is this is because in this video, we are going to go through the theory and how to solve one of these complete linear analysis, accounting for all the loads, all the displacements, everything. And then in the next video, we're going to do the exact same analysis of the exact same elements, but we're going to do it in the finite element program Abacus. And the reason why is because what you guys are going to see is this analysis and the one we do in Abacus are going to yield the exact same results. This is very important because this will allow you guys to have a good understanding of what Abacus is actually doing when you guys run your analysis. It's not very good to just run an analysis, get your results, and say, I have good results. You guys should really know what Abacus is doing in the background so that when you get your results, you guys can make sense of them. Okay, does this make sense? Is this logical? Is this reasonable? Etc., etc. Now, I got to warn you guys really quick. It's probably going to be a little bit of a long video. Again, it's a complete linear analysis of a system. So grab some popcorn, grab some pop, get comfy, get nice and cozy. So with that being said, let's jump into the example and get started. So again, we can see our element here, and we basically have a bunch of parameters that we need to characterize. So this is going to be the first part of my Mathematica code here, is I'm just going to go through all the parameters listed and kind of store them. So I'm going to come down right here, and the first one I'm going to do is I'm going to create a section called element parameters. All right, nice and simple. So element parameters, this includes, to me at least, again, you guys can do these all in one set of parameters if you guys want. But to me, element parameters include two things, the element geometry, as well as the element material properties. So I'm going to start with the geometry, and the most simple thing is going to be the coordinates. So I'm going to go coordinates, and what I'm going to do is I'm actually going to make a vector, and inside of the vector, I'm going to store each coordinate point. So my overall vector is the two squiggle brackets at the end. And as you guys see inside, I included two sets of squiggle brackets 4 times. And what I'm going to do is I'm going to input the coordinates of each of the nodes into each one of these. So before I do that, I'm going to have to separate them with a nice comma, just like that. And then I'm just going to go around in a counterclockwise format to store all of these coordinate points. So we see that our first coordinate point is going to be at 0, 0. Moving over to the next one, it's at 3, 1. To the next node, it's 3.5, 3.2. And then our final node is 0.5, 3. So if I were to just go matrix form really quick, just to show you guys what's going on, all I did was store all the elements, coordinate points. So we have our first coordinate point, our second, our third, and then of course our fourth. I was going to say fifth, but that's not our fifth. You guys are doing an example with someone who obviously can't count. So this is going to be representing the shape of the element in our 2D plane. But of course, we know that our element is almost essentially a 3D element. We are just trying to model it in a 2D plane. And what I mean by that is we know that the element has a thickness into the page, or in this case, into the screen. So we're also going to have to account for that thickness. And I'm going to call this thickness t, and we are just going to say that t is going to be equal to 1. Nice and simple. So this right here, this is the complete geometry of our element. We have all of our coordinate points in our 2D plane, and then we have that thickness into the screen. So this is all we need in terms of geometry. Now we move on to material properties, and there's basically going to be 3 that are of interest to us. The first one is going to be our Young's modulus. So I'm going to go EM, not E comma, EM, and it's blue, meaning it's undefined. So if I were to just go E, as we can see, Mathematica has it as black, which means that it's actually already defined. So we can't use E by itself. We have to go to a variable that's undefined. That's why I go EM. And in this particular example, it is set to unity. So EM is simply going to be equal to 1. And then usually accompanied by the elastic modulus in these linear analysis is the Poisson's ratio nu. So I'm going to call nu as V, and we are just going to say it's equal to 0.3. Again, this comes right from the example, so that's not too bad. Now, when we're looking at this particular example, it's unique in the sense that it has a gravity loading. And of course, the gravity loading, or the loads created on the element due to gravity, they are actually going to be a function of the mass of the element. So another thing that we're also going to include under this section of parameters is the density. So I'm going to call our density in this case P, which it's the closest it looks to rho basically. And we know that our density in this particular example is just going to be set to 1. So I'm going to go Shift Enter really quick, kind of get rid of that results down at the bottom. And we can say that we've now defined our element parameters. Now what I'm going to do is I'm going to come down, I'm going to create a second section of parameters, but this time I'm going to call these our loading parameters, because of course we have our element, but we are subjecting our element to some sort of loading. Now when we're dealing with loading in a linear analysis, we basically have 3 types of loading that we're going to have to be on the lookout for. The first one is any concentrated loads. So I'm going to call this P. And these are concentrated loads that are already directly applied to our nodes. So I'm going to go P is equal to, and then I'm going to create a vector. And basically, I'm just going to go through each degree of freedom of the system. And if there's a concentrated load there, I'm just going to include it into this P vector. So if we look at node 1, it's a fixed node, so there's no concentrated loads. I'm going to have this as 0, 0. This is the horizontal component of node 1, and this is the vertical component of node 1. Moving on to node 2, it's also fixed, so there's no concentrated loads. I'm going to put 0, 0 again, because again, this is the horizontal component of node 2, and this is the vertical component of node 2. Now, if we move on to node number 3, we actually see that we have 2 concentrated loads. We have a concentrated load of 2 going in the horizontal direction, and then we have a concentrated load of 2 going in the vertical direction. So for node 3, I'm actually going to go 2, 2. Nice and simple. And finally, when we move on to node number 4, we see that it is, again, no concentrated loads, so I'm going to go 0, 0. So if you guys do this correctly, you should have an entry for each degree of freedom of our element. In this case, we have 8 degrees of freedom. We have 8 entries in our vector. This is good to go. And this again is probably the most simplistic of loading, because when we assemble our nodal forces vector, we just take P as it is. We don't really need to manipulate it too much at all. Now when we move on, there's 2 other types of loading, and these are the more complex ones. The first one is our body forces vector, so this would be things like gravity, and then the third one is a traction vector, so this would be things like a distributed load. Now, we know from gravity, as well as our traction vectors, that these act kind of over an element. It either acts over the volume of an element, or it acts over the surface of an element, which is a problem, because when we're doing these linear analysis, we want everything in terms of those nodes. So what we're going to have to do is we're going to define what these traction vectors, in addition to what these gravity loads are, but later on, we're actually going to have to modify them so that those loads act at the nodes rather than the element as a whole. So I'm going to start with B, and this will be the acceleration component of my body forces vector, and I'm going to say that this is equal to 2 components. Basically, the first one is going to be the acceleration in the horizontal direction, and we know that gravity doesn't accelerate anything in the horizontal direction, so this is going to be equal to 0. Now the second one would be, of course, the acceleration in the vertical direction, so this is where you guys would put something like gravity is equal to negative 9.81. But for the simplicity of this example, we are just going to go negative 1. So again, if you guys were to do gravity, this is where your gravity component would go into. And that's it for the body forces vector. But again, of course, we're going to have to modify this later on so that we can have our loads located at our nodes. And then finally, the other vector we talked about is a traction vector. So again, this would be things like a distributed load, something like that. So if we look at our example here, we can see that we actually do have a distributed load acting on the surface between nodes 2 and 3, and it has a magnitude of -1. So in this case, I'm going to go our traction vector is equal to a vector, and it's going to have two components. The first is going to be the horizontal component of this distributed load, which we know is -1. And the second is going to be the vertical component of this distributed load, which we know is 0. So I'm just going to go -1, 0. Now again, much like our body forces vector, we are going to have to manipulate this vector a little bit later on so that we can account for this loading in terms of those nodes. So that's not going to be too bad later on. So I'm going to suppress that, and then we can move on to our final section of parameters. And this one's going to be a little bit different, of course, but that is going to be our constitutive relationship. And I'm not sure if I spell anything wrong. I apologize if I do. I'm an engineer, not an English major, so there's a very good possibility I'm going to start spelling everything a little bit wrong. Now, this is something that we mainly are concerned with when we're dealing with a 2D case. Because in a 2D case, we always have to specify, are we dealing with plane stress, or are we dealing with plane strain? Well, in this case, we're going to be dealing with plane stress, but what I'm going to do is I'm going to create the code so that we can easily swap between the two. So what I'm going to do is I'm going to create the matrix representing the constitutive relationship of plane stress. So as we can see on the screen here, as we covered in previous lectures, we have a nice relationship between the stresses and the strains if we're dealing with the plane stress element. So I'm just going to come down. I'm just going to create that matrix. So of course we have our elastic modulus, and this is divided by 1 plus the Poisson's ratio V. And this is kind of our coefficient out in front. And then we are basically going to multiply this by a 3x3 matrix. So I'm going to put squiggle brackets right here to represent I'm doing a matrix. And inside of this matrix, I then input the components of the matrix. So what I'm going to do is I'm going to have my first row, my second row, and my third row. And inside of each one of these rows, we're going to have commas to separate each of the entries. So I'm first going to put in our commas to separate the rows. And then I'm just going to simply go down the rows. So our first entry we know is simply going to be 1 divided by 1 minus the Poisson's ratio. Oops, I kind of went outside. Our second entry is going to be our Poisson's ratio divided by 1 minus the Poisson's ratio. And finally, our third entry in that row is simply going to be 0. Now moving on to the next row. Again, nice and simple. We're just copy and pasting more or less. We're going to have the Poisson's ratio divided by 1 minus the Poisson's ratio. Then we're going to have 1 divided by 1 minus the Poisson's ratio. And our final entry is going to be 0. Our third row is the easiest. The first two entries are going to be 0. And then finally, we have 1 minus 2 multiplied by the Poisson's ratio and then divided by 2. Gets a little bit more gross, but if we were to just run this really quick, we already have our constitutive relationship between stress and strain. Because if we were to look at our matrix here, we can see that it's only a function of our elastic modulus, which we defined above, as well as the Poisson's ratio, which is also defined above. So this is why we actually have no unknowns in this relationship at all. So I'm going to suppress it, get it out of the way, and I'm not going to bore you with the details of me typing in the plane strain relationship. So what I'm going to do is I'm just going to cut to when I already have it inputted. All right, so now I have the plane strain inputted. We are good to go. So what I like to do is I like to just say, all right, my relationship that I'm going to use, which I'm going to call CC, I am just going to specify whether it's going to be plane stress or plane strain. So in this case, we're dealing with plane stress. So I'm going to go C stress. Nice and simple. If I wanted to, what I could do is I'm going to say, all right, well, if I want the analysis in plane strain, all I'm going to have to do is change this to strain. Nice and easy. But in this case, we're dealing with stress. If you guys know that you're only going to ever be considering plane stress, well, then you can just get rid of this strain matrix. Again, this is just for simplicity if we want to use the code later on to do some modifications. So that's it for our parameters that we've defined. Again, just a little recap. We've defined the element geometry. we define the element material properties, we define the loading on our element, and then we define the constitutive relationship between stress and strain of our element. So that was quite a bit for just our elements, but now we can move on to the fun stuff. So now what I'm going to do is I'm actually going to start dividing the analysis into steps. Now, the first two steps, it doesn't matter the order in which you take them in. One of them is going to be solving for the stiffness matrix, and the second step is going to be solving for our nodal forces. Now, again, like I said, it doesn't matter the order. If you guys want to solve for your nodal forces first, and then your stiffness matrix, you guys can go ahead and do that. That's one of the nice things about a linear analysis. So what I'm going to do is I'm going to create a section called step 1, and for me, I like to find the stiffness matrix first. So I'm going to go stiffness matrix, and then all we're going to do is simply use everything we learned in our previous videos to find this stiffness matrix. So the first thing that we need to do is we need to define our shape functions. Now, what's nice for us is when we're dealing with these isoparametric elements, our shape functions are always going to be the exact same, which is great for us. Now, if we look at our specific example, we're dealing with the 4-node quadrilateral element. So if this was your case, all you guys have to do is go back to the videos, or if you want, go to a textbook, really anywhere, because they're always going to be the same, and just input the shape functions for a 4-node quadrilateral element. There's going to be 4 of them. So what I'm going to do is I'm going to say our first shape function. Well, we know that this is going to be 1 minus z multiplied by 1 minus eta, and then of course divided by 4. And if you guys don't know where this comes from, I will have videos in the description of everything that we cover in this particular example. So this is our first shape function. What's nice is the remaining shape functions actually have more or less the exact same form as this. So to save some time, I'm just going to copy it. I'm going to come down here and I'm going to paste it 3 times because we have 4 shape functions. And then I'm just going to modify the parameters. So of course, the second row will be shape function 2, shape function 3, and then shape function 4. And then the only difference between these is going to be where the pluses and the minuses are. So in the second shape function, this is going to be a plus. In the third shape function, they are both going to be a plus. And then in our fourth shape function, this last entry is going to be a plus. So now if we look at them, all the shape functions are unique. They're all different. Good to go. So what I'm going to do is I'm going to create a vector, which I'm going to call ni. And this is simply just going to be a vector of our shape functions. So we're going to have n1, n2, n3, and n4. So I'm going to suppress that, and we are good to go. Now, the next step is kind of the most important step when we're dealing with these isoparametric quadrilateral elements, and that is going to be our coordinate mapping. Coordinate mapping. And the reason why we have to do coordinate mapping is this. If we were to scroll up, our element parameters, or our element coordinates right now, they're in terms of x and y, or x1 or x2, whatever that global coordinate system is defined in. This 3, 1, well, this is basically 3 units in the x direction, and then 1 unit in the y direction. However, when we look at our shape functions here, we can see that they are a function of z as well as eta. They're not a function of x and y. So what we're going to do in this coordinate mapping section is we're actually going to create a relationship between that global system of x and y and this natural coordinate system of z and eta. Now, it sounds really complex, but it's actually nice and simple. So what I'm going to do is I'm going to come down, I'm going to scroll down a little bit just to make it easier for you guys, and now I'm going to display the equations on the screen. As we can see, it's nice and easy. If I wanted my coordinates of x and y, it's simple. All I need to do is multiply the x and y coordinates, which we defined above, by the corresponding shape function, and then sum all together. So what I'm going to do is I'm going to create a vector called coordinate map, and I'm simply just going to make it as x, y. Not a, y, x, y. And this is going to become a little bit more apparent in why we're doing it in the next step. So we're going to start off with x. So we know that x from our formula is the summation of a particular shape function multiplied by its corresponding coordinate. So what I'm going to do in Mathematica is I'm going to use the sum function. So I go sum, capital S, and then 2 square brackets. Now inside of the square brackets, this is where I start inputting everything. So the sum function, we need 2 inputs. So I'm going to separate those 2 inputs with the comma. The first one that goes on the left side is going to be basically what is the function we're trying to sum, and then on the right side it's where are we summing from. So for this one it's actually kind of simple. We know that we're going to sum from 1 all the way equal to 4. The reason why we have 4 is because we have 4 different shape functions. Because again, if we look at our formula on the right, we basically go n1 times coordinate 1 plus n2 times coordinate 2 plus n3 times coordinate 3 plus n4 times coordinate 4. So this parameter right here will always be the number of shape functions you have. If you go on to do an 8-node element, this would then, of course, change to 8. Now, the summation function is nice and simple. What we are going to do is we are going to take the ith component of our shape function vector. So in this case, when we start off with I equals 1, it's going to take n1. If we go I equals 2, it's going to take n2, etc., etc. And then we are multiplying this by the respective coordinates. So when we come to our coordinates, we know that we actually have two things to consider. We have one entry here and one entry here. So if we look here, this second entry, scrolling up, this basically means, are we going to take the horizontal component or are we going to take the vertical component? So for the second entry right here, we know that in this particular case, if we're dealing with x, we always want the horizontal component. So this will always be 1. Now from here, this is where we input our actual iteration. So this is where we would have the I. So again, if I were to show you guys a quick example, if I was equal to 1, what this component right here would be an I of I. Well, this is going to be our shape function 1. And then this coordinate I comma 1, this would be the horizontal component of our first coordinate. So this would be 0. If I were to come down here and move on to I equals 2, well, ni of 2 is going to be our second shape function now, and then multiplied by coordinate 2 comma 1. So that would be the horizontal component of our second coordinate right there. So nice and simple. So I'm going to suppress that. And what I'm going to do is I'm going to do the exact same thing for the y component, because as you guys can see on the screen, it is the exact same. So I'm going to come down here, just copy and paste it, and I'm going to swap this to y. So instead of x, I got y. Our shape function, this is going to stay the exact same. Now the only difference is instead of a 1 here, and again, this 1 basically ensures that we are only taking the horizontal components, we are going to switch this 1 over to 2. And what this means, instead of taking the horizontal components, we are now only taking the vertical components. So what I'm going to do to show you guys what exactly this coordinate mapping does is to substitute some values in our natural coordinate system, because if I were to look at my coordinate map right now, as we can see, it's a function of z and eta. So this is our natural coordinate system. So what I'm going to do is I'm going to substitute some values from our natural coordinate system and see what pops up. So the first one I'm going to do is z approaches -1 and eta approaches -1. Now, if you guys remember from the theory, this corresponds to node number 1. So if I were to run it really quick, I get 0, 0. Now this makes sense because if I come up, our first coordinate is actually 0, 0. Now, if I were to look at node 2 over here, we know that node 2 in our natural coordinate system occurs when z is equal to 1 and eta is equal to -1. So if I were to run that, I get 3, 1. I come up here, I get 3, 1. And I can do the exact same thing for node 3. So node 3 occurs at z is equal to 1, eta is equal to 1. I get 3.5 and 3.2. So if I were to come up here, 3.5, 3.2, I hope by now that you guys can trust me that this coordinate mapping system makes sense. Good to go. So after we do that, what I'm going to do is I'm going to create our n matrix. Now you guys may be saying, Clayton, what exactly is this n matrix? I kind of forget. Well, this relates our displacement field, so our displacement across our entire element, to our nodal displacements. That's kind of the name of the game here when we're dealing with these linear analysis, is that we always want to find those nodal displacements. However, what I want to do is I want to relate the displacement across the entire element to those nodal displacements. And it's actually really simple because all we need to do is follow the formula on the screen here, where we're basically taking a matrix full of our shape functions and then multiplying it by those nodal displacements. So in this section here, I'm just going to create that matrix full of shape functions. So what I'm going to do, I'm going to call this nn, because if we look at n, it's already defined and we don't really want that. So I'm going to call this nn. And what I'm going to do is I'm just going to make an empty table to start us off. So I'm going to use the table command in Mathematica, and we want it just full of zeros. So I'm going to go 0 here, and then I'm just going to dimension the size of this table. So if we look, it has 2 rows. So I'm going to go I from 1 to 2, and then if we look, it has 8 columns. So I'm going to go I oops, not 1, I from 1 to 8. Now, it may be a little bit confusing, so what I'm going to do is I'm going to throw this in matrix form, and this is all I did. I created a table full of zeros. It had 2 rows, so I went from I equals 1 to 2, and then it had, of course, 8 columns, so I went from I equals 1 to 8. Now, you guys might cringe a little bit, me using I at the same time, so if you guys want, we can change it to J just to eliminate some of that cringe. It's going to give you the exact same thing, though. So I'm going to delete that, and I'm going to move forward. Now what happens is if we look at this, it's just a table full of zeros, nothing too special. But we know that we have to input our shape functions into these entries. So of course we know that this is 0, but it should be n1. This is 0, but it should be n2. This is 0, should be n3, etc., etc. So what we're going to do is we're going to create a loop using that do command. And what the do command is nice is because I'm basically going to go through each one of these entries and I'm going to say what they're equal to. So what I'm going to do is I'm going to start off with these entries right here. So this entry right here, this entry right here, this entry right here, and then this entry right here. We know that it should be n1, n2, n3, and n4. Now what I'm going to do is I'm going to go nn, and I'm going to list its component. So we know that we're always dealing with this first row here, so I'm going to have 1. And then we're always dealing with the second entry in this vector. Now what's nice is there's a nice relationship for the second entry where it is 2 multiplied by I minus 1. And I'll show you guys how this makes sense a little bit later. And basically what we're going to do is we are going to go from I equals 1 to 4. Now this is where it'll start to make sense, hopefully a little bit. If I were to have I equals 1 here, 2 times 1 is 2, minus 1 is 1. So I equals 1, that'll give us this first component right here. If I have I equals 2, 2 times 2 is 4, minus 1 is 3. I have entry 1, 3. That'll be this one right here. I equals 3, 2 times 3 is 6, minus 1 is 5. This entry right here. So as we can see, we're kind of skipping each one. Now what I'm going to do is I'm going to say that that entry right there that we just had a nice relationship for, we know that this of course is going to be equal to our corresponding shape function. So this is equal to n of I. So again, if I were to just show you guys really quick, I equals 1, we have 1 comma 2 times 1 minus 1, which is 1. So we have this component right here is equal to ni of I. If we look at ni, our first component is 1. So this is going to make sense. So if I were to just suppress this again, and I'm going to come down here and I'm going to go nn in matrix form. As we can see, I now have my shape function 1 in the first component, shape function 2 in the third component, shape function 3 in the fifth component, etc. Now what we're going to do is we're going to fill in the bottom row now, and it's actually nice and simple. So we're going to take the exact same code, copy and paste it, but now instead of dealing with the first row, we now know that we're moving on to the second row. And instead of always going from 1 to 3 to 5 to 7, etc., we know that we are going from 2 to 4 to 6 to 8. And this is simple. All we need to do to make that pattern happen is just eliminate the minus 1 right there. So now if I were to run this, as we can see, it kind of goes off screen, but we have our nice entries here. We are good to go. So that's going to be our n matrix. Now, a little fun fact about this n matrix is we actually do not need it when creating our stiffness matrix. Kind of, again, a little fun fact, but we will need it later on when we are defining our loads. So this is why we have it. When we define our loads, we are going to see this n matrix come into play. Now, one thing that we do need when we're defining our stiffness matrix is something called the Jacobian matrix. Jacobian, if I can spell, of course, Jacobian matrix. Now, what this Jacobian matrix does is basically relates the size of the element between the two coordinate systems. So we know in our natural coordinate system of z and eta, our element always goes from -1 to 1 in the z direction and -1 to 1 in the eta direction. This would mean that the length of the element is always going to be 2 by 2, so our cross-sectional area will always be 4. Always. Now, this is a problem because if you think about our global system, our element cross-sectional area could be many different things. It could be 1, which is going to be smaller than our natural coordinate system. It could be 100, which is much larger than our natural coordinate system. So what this Jacobian matrix does is it simply relates those two areas together so that when we are calculating our stiffness in our natural coordinate system, we basically times it by a factor which comes from this Jacobian matrix that accounts for the fact that in our global system, our element can be either much larger or much smaller. So if we look up above, I have our coordinate map as x comma y. I'm going to create kind of a second one, which is our natural, if I can spell natural, of course, natural coordinate. And we know our natural coordinates are a function of z as well as eta. And this will make sense a little bit why I'm doing this in about 2 seconds here. So if we look at our formula for the Jacobian, it's actually nice and simple. It's just a 2 by 2 matrix. So when I'm defining our Jacobian, we are going to use the table command. Now we've already used the table command, and before we said that everything in our table is going to be equal to 0. We're actually not going to do that this time because we know what each entry in our table is actually going to be. But we're going to deal with the other two parts of our table command first, which is basically how many rows do we have? Well, we know that we have 2 rows, so we're going to go I from 1 to 2. And then we know that we have 2 columns, so we are going to go from J is 1 to 2. So if I were to actually just have this as a 0 really quick and run it for you guys, as we can see, we just have a 2 by 2 matrix. Everything in it is going to be equal to 0. But we know, of course, not everything is going to be equal to 0. The actual entries of this Jacobian are a bunch of partial derivatives. So what we're going to do is we are going to use the derivative function. It sounds pretty crazy, but it's actually not too bad. Now, if we look at the formula for these derivatives, we are always taking our global coordinates, x and y, and we're differentiating them with respect to our natural coordinates, z and eta. So what we're going to do is we're going to call upon our coordinate map. You guys are saying, Clayton, what is this coordinate map? Well, it's simply up here. It's simply just x and y. So we're going to take our coordinate map of I, and we're going to differentiate it to this natural coordinate system. So we're going to go natural coordinate system of j. Now you guys looking at this and saying, well, Clayton, this looks kind of crazy. Let's do a quick example. Let's take the first entry of I equals 1 and j equals 1. This will take coordinate map of 1, which is x, and it's going to differentiate it to natural coordinate of 1, which is z. So this first one where I and j is equal to 1, it's basically the same as the derivative of x with respect to z. If I were to go I equals 2 and j equals 1, well, coordinate map of 2 is going to be y, and natural coordinate still of 1 is still going to be z. So this will take all those derivatives that we need. So if I were to throw this in matrix form really quick, we now have our Jacobian right here, nice and simple. Now, another thing that we are going to need for later on that we don't really deal with right now is going to be something called J inverse. Now, it's kind of misleading because it's not just the inverse of our Jacobian. What this is going to be equal to is the transpose of the inverse of our Jacobian. So it sounds pretty crazy, but all I'm doing is I'm taking this Jacobian, which we have down here, I'm inversing it, and then I'm transposing it. Now this will become clear once we deal with our B matrix, which is going to be our next section, because some of the entries of this B matrix are directly related to this J inverse, or this transpose of the inverse of our Jacobian. So I'm just going to express that. And now we are going to move on to the fun one, which is our B matrix. Now our B matrix is something that's very special. As we can see on the formula on the side, the strain in our element is going to be equal to this B matrix multiplied by those nodal displacements. Now for these isoparametric elements, of course, the B matrix gets a little bit ugly. So what I like to do is I like to separate it into 3 components, which I'm going to call B1, B2, and B3. So I'm going to come down here, and I'm just going to get rid of that output out there to make it simple, and we are going to start with B1. Now B1 is actually very nice. It's just a simple matrix of 1s and 0s. So what I'm going to do is I'm going to say, all right, I can see that this has 3 rows. So I'm going to have 1, 2, 3 rows. I'm going to separate each one of the rows by commas, and I'm just going to go across the rows. So of course our first row is 1, 0, 0, 0. Our second one is going to be 0, 0, 0, 1. And then finally our third one is going to be 0, 1, 1, 0. So this is the nicest of them all. It's just 1s and 0s, and it doesn't change. You guys are saying, Clayton, where the hell did that come from? Well, again, I will have links to the theory videos down in the description below. Now we move on to our second one, which is B2, and B2 is where it gets a little bit crazy. As we can see, B2 is just a function of a lot of those partial derivatives. Now, if we look at those partial derivatives, they actually very closely resemble our Jacobian matrix above, but they're actually a little bit different in the fact that they are the inverse of our Jacobian matrix and then transpose. So this is why I defined this right here because the entries of B2 are actually the entries of this J inverse that I defined above. So what I'm going to do is I'm just going to make a very big ugly matrix of B2. So we know that B2 is a 4 by 4 matrix, so I'm going to have 4 rows, so 1, 2, 3, and 4, and I'm going to separate each one of these rows by a comma. Now I'm just going to go down and input each one of these inputs. So if we look at the first component of B2, we can see that it's actually the first component of J inverse. So I'm going to go J inverse of 1, 1. Our second entry is J inverse 1, 2. And then our final two entries are 0, 0. Coming down here, I'm going to go J inverse of 2, 1. Then we have J inverse of, oops, I need double brackets there, 2, 2. And then we have 0, 0. So if we look here, the first and second entry are J inverse 1, 1 and J inverse 1, 2. We move on to the next row. The first two entries are J inverse 2, 1 and J inverse 2, 2. Now, if you guys go back to the theory, you guys see exactly why this is. Our B2 matrix is essentially that J inverse matrix located at two different locations in this matrix. Now we move on to the third and the fourth rows. We know that both of them start with 0, 0, but the next two entries are the exact same as before, as they're J inverse 1, 1, and then J inverse 1, 2. Moving on to the fourth row, again, 0, 0, and we have J inverse 2, 1, and then J inverse 2, 2. Nice and simple. Now, I probably forgot some square brackets, so what I'm going to do is I'm just going to run this bad boy. Oops, I don't know why I did that. I'm just going to run that to get this. Now, another thing I'm going to do is this, just to really hammer in the relationship between B2 and J inverse. I'm going to write down J inverse in matrix form. And as we can see, this J inverse matrix right here, that is exactly the same as this little sub matrix right here, as well as right here. So this is why I was able to go down so fast, because all I'm doing is I'm taking this J inverse, and I know that it's equal to this matrix right here, as well as this matrix down below. So hopefully that makes sense to you guys and why I was able to make it so fast. Now, the last matrix is the B3 matrix, and this one is a little bit funny. And again, just kind of like the N matrix before, this is simply just going to be a matrix full of our shape functions. So what we're going to do is we're going to start off by creating a table full of zeros, just like we did in the N matrix. So we're just going to go from 0. But now instead of having 2 rows, we actually have 3 rows. So I'm going to go I equals 1 to 4. And then when we're looking at the columns, we still have 8 columns. So we'll go J, just so you guys don't cringe, 1 to 8. So if I were to throw this in matrix form right now, just like that, as we can see, I just have empty zeros. Now, of course, we know that we want this one to be N1, N2, N3, or the derivatives of N1, N2, and N3, etc., etc. So what we're going to do is I'm actually going to go up and I'm going to copy the exact same code I did for this N matrix, because it follows the exact same format. The only difference is we're going to have to modify it a little bit. The first modification is we're no longer dealing with NN. Actually, let me get rid of the second one just so we can focus on one. Let me just bring this down. So we're not dealing with NN anymore. We're dealing with the entries of B3. Now this is going to stay the exact same, and then we are going to go from here to here to here to here, etc. But we also know that the derivative here is the same as the derivative here. The derivative here is the same as the derivative here. So instead of saying that just these entries are equal to something, I'm going to say that these entries are equal to another set of entries inside of our B3 matrix, which are then going to be equal to something. Now, another modification that we need to make is that right now it's saying that it's equal directly to the shape function, which we know that's not entirely true. We know that these entries at the top here, all over that first row and all over that second row, they're equal to the derivative of our shape function with respect to z. Now, that's kind of the key thing here. In our first and our third row, as we can see on the formula on the side, so first row and third row, it's always going to be with respect to z. So it's nice and simple. I can just put z in there, no problem. Now, if I were to run this right now, it'll correctly fill in this entry, this entry, this entry, and this entry. But we also want it to do this entry, this entry, this entry, as well as this entry. So instead of dealing with row 1, we know that in our second entry, we always wanted to deal with that third row right here. And for this one right here, we're going from 1 to 3 to 5 to 7. But in the second case, we want 2 to 4 to 6 to 8. Well, we already discussed above that this is simply just going to be 2 multiplied by I. So if I were to run this right now, if I were to run it right now and not suppress it, we can see, oh, that's because I'm running a function. Sorry guys, B3 in matrix form. We can see that we now have our correct entries in all the locations. So this is going to be the derivative of n1 with respect to z in our correct entries, the derivative of n2 with respect to z, correct entries, and then the derivative of n3 with respect to z, etc., etc. But that is only for the derivatives with respect to z. We also know that the second row and the fourth row are the derivatives with respect to eta. So I'm just going to copy this really quick because it's actually going to follow a very similar pattern. And instead of taking derivatives with respect to z, we want derivatives with respect to eta. Now another thing we have to account for is instead of dealing with rows 1 and rows 3, we want rows 2 and rows 4. So instead of dealing with row 1, we want row 2. Instead of dealing with row 3, we want row 4. So that's all I'm going to do. If I were to run it now, as we can see, our matrix look nice and sexy. So I'm going to delete this. I'm going to go up, I'm going to delete that too. And we can see that we now have all three of our little, what I call submatrices, required to find our final B matrix. So B is going to simply be equal to B1 multiplied by B2 multiplied by B3. And if I were to just throw this in matrix form, as you guys can see, it is rather disgusting. So this leads me to one thing: never ever do the finite element method by hand. It is disgusting. You guys will probably make one little mistake, which will snowball. Please don't do it by hand. It's really, really gross. Now, another thing I want to just say really quick is congratulations, we have done the very gross part. This B matrix in our stiffness matrix, it is by far the grossest part. Everything after this actually becomes nice and simple. So what I'm going to do is I'm going to come down here and we can start directly solving our stiffness matrix. So I'm going to have the formula on the screen now. And what I like to do is I like to create our integration function. So basically, this is the function that we would have to integrate in order to find our stiffness matrix. So I'm going to call this our int function. And we know that it is simply going to be, from our formula on the side, this transpose, if I can spell correctly, of course, the transpose of our B matrix multiplied by our C matrix. So this is where plane stress or plane strain actually plays an impact, and then multiplied by our B matrix again. Now, a little thing to keep in mind is in Mathematica, when we're multiplying these matrices, we do a period. We don't do the time sign. As we can see up here too, again, we did the period. Don't do the time sign, you guys will get something wrong. We use the time sign when we're multiplying by some sort of scalar value. And that's exactly what we're doing at the end of our integration function, because we multiply this by the determinant of our Jacobian. So if we were to relate this to our traditional solid elements, this stays the exact same. The only difference is we multiply by this determinant of J to account for the size effect between the elements in our natural and our global system. So I'm going to suppress that. We're good to go. And then we can directly calculate what our stiffness matrix is. So I'm just going to say stiffness matrix, and we have basically three different options. We can actually integrate our integration function. That'll take forever. No one wants to do that. Or we can do Gaussian integration. So of course we're going to do the Gaussian integration, but in the Gaussian integration we have two different options. We have reduced integration or we have full integration. Now what we're going to do is we're actually going to use full integration, and we know that if we're dealing with a 4-node quadrilateral element, full integration requires 2 integration points. So what I'm going to do is I'm going to create those integration points. The first one I'm going to call z set, and I'm going to make it a vector of those 2 integration points. Now what's nice for us is those 2 integration points, they're already defined for us. It's simply 1 divided by the square root of 3 and -1 divided by the square root of 3. Nice and simple. And what's nice for us too is that our integration points in the other direction, so this is z, the horizontal direction. If we were to look at the vertical direction, which is eta, it's actually going to be the exact same thing. So I have z set as 1 over square root of 3, -1 over square root of 3, and then I have my eta set as 1 over square root of 3, -1 divided by square root of 3. So I'm going to suppress those, and I can come down and I can find my stiffness matrix. So I'm going to call this K full, which is the stiffness matrix using full integration. And we know that it's simply going to be that into the page thickness T, which we defined above, multiplied by the sum of our integration function specifically when it approaches those integration points. So if you guys are a little bit confused at what I'm doing, I highly recommend checking out our Gaussian integration section. This describes what exactly we are doing. So what exactly we are doing is we are going our integration function specifically when z approaches z set of I and eta approaches eta set of j. So basically when this function, when we defined above, when it approaches those two integration points, or when it's equal to those two integration points. Now we have to define our summation limits. So of course for z we're going from 1 to 2 because we have two different integration points. So I equals 1 to 2. And when we're dealing with eta, we're also going from 1 to 2 because we have two different integration points. So I'm going to go j equals 1 to 2. Now if you guys are wondering what exactly is going on, well, let's take I equals 1 and j equals 1. It's basically going to be our function, which we have above, when z approaches 1 divided by square root of 3 and eta approaches 1 divided by square root of 3. So this is just our function at one of those integration points. We can move on to the next one. We evaluate our function at a different integration point. And this kind of just goes on and on and on. So what we're going to do now, just to kind of see if we're on the right track, is we are just going to look at our stiffness matrix. And this is our stiffness matrix right here. As we can see, one, it is symmetric, which is expected, and it is 8 by 8, which is expected. So of course, since we have 8 total degrees of freedom for our elements, we have 8 total columns and rows for our stiffness matrix. Now this is where things would change a little bit if we were considering multiple elements. So if we were considering multiple elements, we have our stiffness matrix for each singular element right now. All we'd have to do is we'd have to combine them together to create one sort of global stiffness matrix. Now, in the case of one element here, we just have one stiffness matrix. So in this case, our element stiffness matrix is actually equal to our global stiffness matrix, with some modification for those boundary conditions, which we will do a little bit later. But in essence, step 1 is now complete. We have now found what our stiffness matrix is equal to. We can move on to step number 2, which again, you guys can do a step number 1 if you guys want. And this is going to be our nodal forces vector. Now our nodal forces vector actually has basically 3 different components as we discussed above. So if I were to scroll up, we can see that there is a component due to concentrated loads at the nodes. There's a component due to body forces such as gravity. And then there's a component due to traction forces, such as the case we have here where we have a distributed load. So what I'm going to do is I'm just going to create each one of those components separately. So the first one I'm going to do, which is the simplest, is nodal loads due to concentrated loads. Concentrated. I have to make sure I spell things correctly. I'm an idiot, guys. It's going to be even worse when I say that and then I still spell it incorrectly. So our first component is our nodal loads due to those concentrated loads that we already have at the nodes. So what I'm going to do this is I'm going to call this FA, and we know that this is simply going to be equal to P. This is all we need in this section, because if we look up above here, we've already defined what our concentrated loads at those nodes are going to be. Nice and simple. Down here we can actually get into the fun ones, and the first fun one is of course our nodal loads due to our body forces. Now our body forces are actually going to be a little bit different. So if we look at the formula that we see on the screen here, and actually let me just get rid of that entry down at the bottom so we're not getting too confused. But if we look at our formula on the screen here, we can see that we're basically taking the transpose of our N matrix, which we defined above, and this is why I defined it above up here. We're taking the transpose and we're multiplying it by a component rho b. Well, we defined what rho is and we defined what b is. So what I'm going to do is I'm going to say rho b is simply equal to rho, which we defined above. This is the density of our element. And then we multiply it by b, which is basically the acceleration of our element in each direction. So we're just going to say that rho is equal to, rho b is equal to rho times b, nice and simple. And then what we're going to do here is I'm going to, just like I did before, create an integration function. I'm going to say that our PB function is equal to the transpose of our matrix N multiplied, and remember, we're taking a matrix and we're multiplying it by a vector, by rho b, so this has to be the dot right here. If you guys don't do the dots, something will go wrong. And then we also have to multiply it by the determinant of j, just like we did before, to account for that size effect between the natural and our global system. So I'm going to multiply this by the determinant of j. Now, just like before, we have a bunch of different options to evaluate this function, but we are going to use the full integration scheme we did for our stiffness matrix above right here. So actually, I'm going to copy this exactly. I'm going to take it, copy it, because all we need to do is make the modifications. So rather than the integration function, which was up here, we now know that we are doing our PB function. These integration points are going to remain the exact same. The only difference, of course, is we are going to have to change the name. So instead of K full, we're going to have this as F rho B. So our nodal forces due to our gravity loads. So what I'm going to do is I'm actually going to unsuppress it, matrix form. And as we can see, we end up with basically an 8-component vector. Now what this vector actually represents is the nodal loads due to that gravity force. So as we can see, every second entry is 0, which makes sense because gravity actually doesn't create a horizontal load, it creates vertical loads. So this would be our gravity load at node 1, our gravity load at node 2, our gravity load at node 3, and our gravity load at node 4. So that's exactly what we did. We took basically a gravity load and we converted it into an equivalent nodal load. That's all we did. And we're going to do the exact same process now for our traction vector. So we're going to say nodal forces, or nodal loads, due to, in this case, traction vectors. Now, traction vectors are a little bit weird in the sense that they act over the surface of an element. They don't act over the volume of an element. So everything fancy that we did up here with this Gaussian integration, we actually can't do it with our traction vectors because, again, this Gaussian right here, this Gaussian integration, that was actually used for volumes. So what we're going to do is we're actually going to play with it a little bit. I'm going to start a little bit later on, and we're just going to see what exactly happens. So if we look at our formula, we can see that our traction vector function is simply, just like before, going to be the transpose of our n matrix multiplied by our traction vector. So this stays almost identical to what we had above here, but instead of multiplying by the determinant of j, we actually have to do a little bit funny stuff to it. So in this case right here, this is exactly what we'd have if we were integrating with respect to x, or if we're integrating with respect to y. But of course, we're not integrating with respect to x, or we're not integrating with respect to y. We're actually integrating in our natural coordinate system. So we need to change that dx or dy to d eta or dz. This is very simple because all we're going to do is follow the formula on the side here. We're going to take the exact same thing that we had before, but instead of multiplying by a determinant of j, I'm going to multiply it by a factor dl. Now what this dl basically is, it's going to be d eta divided by dy. So if we look at our distributed load, we knew that it acted over kind of the vertical surface of this element. So what we're going to do is we're going to create a factor called dl. So you guys may be wondering what dl is actually equal to. Well, it's actually not too bad. dl is actually going to be equal to the square root of the derivative of x with respect to eta. And then this is going to be squared. So this all comes from basically a triangle, plus the derivative of y with respect to eta, also squared. Now, one thing that we have to consider in our natural coordinate system is that we're integrating over basically a vertical length. So at this length right here, we can see that z is always going to be equal to 1. That's going to be one of the key here. So what we're going to do is we're also going to say specifically when z approaches 1. Because again, this traction vector acts in our natural coordinate system always at a location of z is equal to 1. So if I were to suppress this really quick because I don't want to see it, we can see that this dl right here is basically just a factor counting for that change in length of the side of the element between our global and our natural coordinate system. Now once we have that, it's actually not too bad at all, but we actually have to use actual integration. So what I'm going to do is I'm going to say ftn, which is our nodal load due to our traction vector. Well, this is going to be that into the page thickness t, and then we're going to multiply that by the integral, if I can spell it correctly, integrate of basically that function we defined above, so our tn function, and then we are going to do this from eta, which is again in our natural coordinate system our y direction, from -1 to 1. So we're just integrating over the surface in which that traction vector acts. Now again, Another thing we have to keep in mind is this surface always occurs for this particular traction vector when z approaches 1, or when z is equal to 1. So this is one of the things that we have to kind of take into account. So if I were to run this right here, well, actually, I'll throw it in matrix form so you guys can really see what's going on. Again, we end up with an 8-component vector, and this is basically going to be the nodal loads due to this traction vector. Now, this traction vector actually acts between nodes 2 and 3, so it makes sense that nodes 1 and 4, they have no components. Now, if we look at node 2, it now has a horizontal component, and node 3 also has a horizontal component. So that's all we did there. Now, oops, suppressing a comment makes no sense at all. Now, our total nodal force vector, this is simply going to be equal to the summation of our nodal loads due to concentrated loads, our nodal loads due to body forces, and our nodal loads due to traction vectors. So I'm going to call this Fn, and this is simply going to be equal to Fa plus F rho b plus Ftn. So if I were to run this right now, and I'll throw it in matrix form just to really show you guys what's going on, these are going to be the total loads on our elements. All right, so at degree of freedom 1, so the horizontal component of x1, 0 load. We look at degree of freedom 2, so the vertical component of node 1, we can see that we have a load there due to gravity, and then so on and so on. So I'm just going to suppress that really quick, and we can move on to our next step. So at this point right here, we found our stiffness matrix K, we found our total nodal loads F. We can move on to the third step, so I'm going to call this one step 3, and we can say we're going to solve the system for the nodal displacements. Because again, this is one of, I was going to say distances, displacements. And this is kind of the one thing that we've always talked about, is this is what we're doing, is we're solving the system for those nodal displacements. And solving the system, it's actually really simple. All we have to do is use a nice linear equation. Now, before we do that, we actually have to account for the boundary conditions. Account for boundary conditions. Because as we see in our example, node 1 and node 2 are completely fixed. So what happens is when we have a fixed degree of freedom, what we do is we actually remove that column and row from our global stiffness matrix. So I'm going to have a global stiffness matrix here, and it's actually going to be equal to, and I'll show you guys what I'm doing in a second, is actually going to be equal to our element stiffness matrix, but we're going to remove some of those rows. How do I do that? Well, I'm using the drop function in Mathematica. What this will do is basically I can specify which entries of this matrix I want to remove. Now, when we're looking at the rows, we know that node 1 and node 2 are fixed. Therefore, degree of freedom 1, 2, 3, and 4 are all fixed. They don't move. So what I'm going to do is I'm going to go 1, 4. And this will remove rows 1 to 4 in this matrix. But we know that we only don't remove the rows, we also remove the columns. So I'm going to create a second vector over here, and this will also be 1 to 4. Whatever I remove in terms of rows should always be identical to what I remove in terms of columns. So if I were to throw this in matrix form really quick, we now have a 4 by 4 matrix. Now what I'm going to do is I'm also going to show you guys K full to show you guys what exactly we removed. Oops, forgot the double slash there. All right, so basically we said that degree of freedom 1, 2, 3, and 4 were removed. So what we're doing is removing, we're removing this, we're removing this, we're removing this, and this in terms of columns, and removing the first, second, third, and fourth row in terms of rows. So what we should only be left with is this little bottom portion down here, and that's exactly what we have. So we start at 0.31874, that's what we have, and we're going down to 0.5848, that's what we have. So again, I just removed all these because in terms of boundary conditions, we know that there is no displacements because we fixed them. So I'm going to delete that, and we have to do the exact same thing for our nodal forces vector. So what I'm going to do is I'm going to create a vector called F global, and I'm going to drop basically the exact same entries. So from our nodal forces vector, I am going to drop basically entries 1 through 4. So 1, 4. If I were to do this in matrix form, we have this. And this makes sense because even though I had components in nodes 1 and 2, they are acting directly at a support. If I were to place a load directly at a support, we know it goes directly into the support. It doesn't actually displace our system at all. So these are the two vectors that we need to actually solve our system. Because what we have is we actually have a linear system. So we're going to do solve the linear system. Nice and simple. And Mathematica has a nice command. So we're going to say ndisp, this will be our nodal displacements, is going to be equal to linear solve. So this is going to be the function that we are going to use to solve our linear system. The first entry is going to be the matrix, so this will be k global. And then the second entry is going to be our vector, so this would be f global. So if I were to run this really quick, as we can see, I get a vector right here, and what I'm going to do is throw it in matrix form. I get the following, and that does not quite look right. So hold on one second, guys. There's something a little bit iffy in our code. That's good. That's good. That's good. Ah, right here. I must have made you guys cringe for the whole video. So in plane stress, this last component is simply 1/2, but I put it as the component for plane strain. So if I were to run this bad boy now, that looks much better. We now have our nodal displacements. This would be the horizontal displacement at node 3. This would be the vertical displacement at node 3. This would be the horizontal displacement at node 4. And then this right here would be the vertical displacement at node 4. So this is how we find those unknown displacements. Now what I'm going to do is I'm actually going to go back and I'm going to create another nodal displacement vector. But what I'm going to do is I'm going to create the vector in terms of all the nodal displacements. So nodal displacement vector. Because if we look right here, we only have the displacements at nodes 3 and 4 basically. So what I'm going to do is I'm going to create a vector called nodal displacement. And what we're basically going to do is we're going to create the full vector for all 8 degrees of freedom. Now what's nice is we know the unknown degrees of freedom, so nodes 3 and 4, and we know that the displacement at node 1 and 2, well, they're simply going to be 0 because they're fixed. So I'm going to use the insert command to basically insert zeros into our end displacement vector. So this end displacement, if I can spell it correctly, of course, this is the vector we have down here. And again, this is node 3, these first two, and these two are node 4. So what I want to do is I want to add zeros before that to account for the fact that node 1 and node 2 all have 0 displacement. So what I'm going to do is I'm going to insert zeros, and then in the next tab I can specify where I want those zeros to be. So what I want to do is I want to insert a 0 for the first entry. So if I were to do that, and I'll keep this in matrix form actually so you guys can see what's happening, I now put a 0 before. So this would be the horizontal component of node 1. Now what I'm going to do is I'm going to add another entry, and again I always want to keep adding my zeros at the beginning. So I'm going to have another one. It's going to be 1, so I now have 2 more zeros. I'm just going to repeat the process for the remainder of the degrees of freedom. So now I have my actual nodal displacement vector. Now what's nice with this vector is I can actually return to my system and solve for the reaction forces. So again, I now have all the displacements, I have a stiffness, but I actually don't have the reaction forces of those boundary conditions. So I'm going to come down here and I'm going to go reaction forces. Nice and simple. Now what's nice is our reaction forces, or I'm going to say my nodal forces to start with, they're simply just going to be equal to our stiffness matrix, which we have as K full. So this is 8 by 8. And then we multiply this by our nodal displacements, which we just defined above. So nodal displacements, so if I run this, these are going to be the forces in the system. Now the thing that we have to keep in mind is when we look at our reaction forces there, they have our forces in the system, but they also consist of the forces that are directly applied to those boundary conditions. So one of the things that we have to remember is that we said when we defined our gravity load, some of that gravity load goes right into the support. So those support reactions have to account for that gravity load. How do we do that? Well, it's actually nice and simple. So reaction forces are actually equal to our nodal forces that we just found above minus our applied nodal forces. So if I were to run this, as we can see, we get a vector right here, and it looks a little bit sketchy at first because we're getting non-zero entries into basically degrees of freedoms that aren't fixed. But as we can see, they're entirely small. So what I'm going to do is I'm just going to use the chop command. And what the chop command does is it basically eliminates entries that are basically 0. So if I do that and I throw this bad boy into matrix form, I get the following. So this would be my horizontal reaction force at node 1 my vertical reaction force at node 1, my horizontal reaction force at node 2, and then my vertical reaction force at node 2. And of course, we can see that node 3 and 4, they have 0 reaction forces. And this makes sense to us because we know that we actually did not fix them. So that's going to be our reaction forces. Now this concludes step 3, and this is where students usually stop. They say, all right, I have my stiffness, I now have all my unknown displacements, and I also have all my reaction forces. So if I was doing some sort of structural analysis, I'm thinking, you know what, I'm pretty good. I have my displacements at certain spots, and I have my reaction forces at the reactions. But now we have to realize that one of the most beautiful things that we have in the finite element program is the fact that we can take these nodal displacements that we now have and we can use them to find the displacement, the stress, as well as the strain inside of our element. So what we're going to do is we're going to come down here and I'm going to create step 4, which is the displacement slash strain slash stress inside of the element. So this is one of the most beautiful things about that finite element method is once we have those nodal displacement, we can take it a step further in structural analysis and we can actually solve for so many things inside of our element or between those nodes. So what we're going to do is we're going to come down here, and the first thing that we're going to do is we're going to have displacement inside of the element, just like this. And we remember from our equations before that the displacement inside of an element is simply going to be that n matrix, which we defined above, multiplied by those nodal displacements. As we're going to see, now that we have these nodal displacements, it opens up a world of possibilities. So I'm going to say element displacement. Well, this is going to be equal to the transpose, or sorry, not the transpose, that was for the forces. This is going to be our n matrix multiplied by those nodal displacements. Nice and simple. So if I were to run this really quick, I basically have a function. It's so hard to tell when it's written like that. I basically have a 2-component vector. This right here is going to be basically the displacement in the horizontal direction, and this right here is going to be the displacement in the vertical direction. So all I need to do is substitute at what location in my element in terms of eta and z that I'm interested in, and this will return me with my element displacement. Now we can move on and say, well, we can do the exact same thing for the strain. So I'm going to go strain inside of the element, just like this. And we know that our strain, as we discussed before, is simply going to be that B matrix multiplied by our nodal displacements. See, as I've been saying, those nodal displacements, very powerful because they allow us to do so many different things. So this right here actually returns us with a 3-component vector. It's hard to see because it's so long, and this makes sense. So this entry right here, this will be epsilon 1, 1 at any location we like. This right here will be epsilon 2, 2 at any location we like. And then this right here will be epsilon 1, 2, or a shear strain at any location that we like. So that's also looking very good. I'm going to suppress these so we're not getting too many outputs on the screen. And the final thing we can do is we can find the stresses inside of the element. And how do we do that? Well, we know that stresses actually follow a nice relationship in these linear elastic analysis because it's just based on strains. So we know that the stresses is simply going to be our C matrix, our constitutive relationship, multiplied by our strain vector. So if I were to do that and then throw that into matrix form, again, we have a 3-component vector. This will be sigma 1, 1, this will be sigma 2, 2, and this will be sigma 1, 2. And again, they're in terms of eta and z, so I can pick any point inside of my element and estimate those stresses. Very, very beautiful. So what I'm going to do now is I'm just going to do a little bit of post-processing so I can display the results. So I will cut the video and I'll show you guys once I'm done doing that. Alright guys, so we're back and all I did was this. It looks really crazy, but it's really simple. Remember that we now have this strain at basically any point that we want in our element. So what we're going to do is we're going to find the strain components at our integration points. So I picked the location when z approaches -1 over square root 3 and then eta approaches 1 over square root 3. And I did the same thing for all 4 of the integration points in terms of strain. Now I did the exact same thing in terms of stresses. Again, I just found the stresses at the integration points. Now a couple of questions. Clayton, why are you evaluating it at the integration points? Well, this is actually going to be part one of basically a two-part analysis, where in the next video we are going to explore the exact same situation in Abacus, and we are going to compare the results. So in Abacus, what we can do is we can actually very easily find the stresses and the strain at the integration point. So what I did here is I just found it in terms of how Abacus would find it, so that when we get into the next video in doing this in Abacus, we can very quickly make conclusions. Is it accurate to Abacus? Is it different from Abacus? Etc., etc. And that's why my integration points are a little bit wonky too, because normally our first integration point is -1, -1. But as you guys can see, I have -1, +1. Again, I'm just following sort of Abacus's format so that when we make the comparisons in the next video, it goes off rather smoothly. So if I were to run all this right here is just some post-processing to display our results. We have our element stiffness matrix. We have our nodal forces vector, we have our nodal displacements, we have our reaction forces, and then we have basically the strains at our integration points. So these are what we're going to compare into Abacus a little bit later, and then our stresses at the integration point. So again, these are what we're going to compare with Abacus in the next video. But that's it for this video, guys. I hope I was able to help you guys understand kind of the general process of these linear analysis. I hope it was at least somewhat entertaining. I know that this can be really boring. You guys are probably a little bit more excited for the next video when we do it in Abacus. Abacus is always a little bit more fun because we can add a little bit more color. It has the nice sexy contour plots, etc. But it's very important to know what exactly is going on in the background of Abacus. So that's the goal of this video right here. I want to show you guys what exactly Abacus is doing so that when you guys run your own analysis, you guys can say, oh, okay, this makes more sense. It's not just this black box that I throw things into and it gives me outputs. I actually know what's going on behind the scenes. So yeah, I hope I was able to help you guys somewhat at least. Thank you guys so much for listening. I really appreciate it. I will see you guys in the next example video.